Suppose we want to define a function of two variables, but this time over a bounded region that's not rectangular. So again we subdivide this region R into a small number of rectangles, but as we can see, we cannot fill the region with a finite number of rectangles that lie entirely inside this region. So we can see at the boundary, parts of the rectangles lie outside the region. So we form a partition of R using the rectangles that are completely inside R, such as this rectangle for example, this one, and so on. So if we choose a point inside a rectangle with coordinates xi and yi, where we index the rectangles using the index I. So for this particular rectangle, we evaluate the function at this point and multiply by the area of the rectangle. Then taking the sum over the number of rectangles that are completely inside the region, so we sum from I equals 1 to n, then that gives a Riemann sum. So recall the Riemann sum can be different depending on the point we choose inside the rectangle to evaluate the function. And again, if we take the limit of the Riemann sum as the number of rectangles lying completely inside the region approach infinity, then the limiting value will be the double integral of the function of x and y over the area of the region. So noting that for a continuous function, any Riemann sum we choose will converge to the same limiting value, being this double integral of the function over the region R. So note that to get a good approximation to the area of this region using rectangles, then the portions of the rectangles that lie outside the region must become insignificant as the number of rectangles used to approximate the area of the region go to infinity. So as the number of rectangles increase, then the area of each rectangle approaches 0. So this limit is valid where the boundaries are simple, like boundaries that are polygons, circles, and continuous graphs over some interval. So for example, we may have a boundary comprising a continuous curve on both sides, and these graphs of the continuous functions are connected by lines that are parallel to the x-axis. But boundaries, such as those with fractal shapes, cause problems with the convergence of this integral. So they may look something like this. So fractals are repeating patterns. So these are rarely encountered, and therefore we're not going to evaluate the integral for regions with these types of boundaries. We're going to look at a stronger form of Fubini's theorem for general regions that are non-rectangular. So suppose we have a region that's bounded by two lines at y is equal to c and y is equal to d. So in other words, y is inside this closed interval, and the other bounding curves of the region look something like this. So they're continuous functions of y. So we also have g2 of y. So these constitute the boundary of the region. And these two functions describing the boundary are continuous on the closed interval from c to d. Then we can evaluate a double integral of a continuous function of two variables over the area of this region using iterated integrals. So what we can do first is integrate the function with respect to x. So essentially taking a cross section that touches these two curves and it's bounded above by the surface. So it looks something like this. So we're breaking up this cross section into thin rectangles along the x-axis, and integrating with respect to x. So this integral is evaluated from the curve g1 of y to the curve g2 of y. So as we can see, our limits of integration are now variable. And this gives an expression for the area of this cross-section as a function of y. And therefore, we then integrate from y equals c to y equals d. So for a positive continuous function, being f of x and y, over this region in the xy plane, then the volume of the solid region that's bounded below by r and above by the surface, defined by z as a function of x and y, is defined in the same way as for a rectangular region. So therefore the volume of the solid region is given by this double integral. And in a similar way, if the region is bounded by straight lines, where the straight lines are instead perpendicular to the x-axis, so we have x equals a, and this line is at x equals b, so x in this case is inside the closed interval from a to b, and the functions defining the remaining curves of the boundary are continuous on this interval. So these functions will be functions of x. Then we instead take a cross-section that's parallel to the y-axis and integrate the function with respect to y first. So for example, the cross-section in this case may look something like this. So we're first taking the integral with respect to y to obtain the area of this cross-section. And therefore we're integrating from g1 of x to g2 of x. So these are our variable limits of integration. So once we get the area of this cross-section that's perpendicular to the x-axis as a function of x, then we integrate from the line x equals a to x equals b with respect to x. And that's the other way that the double integral is defined, by reversing the integration. So essentially both of these iterated integrals give the same volume of the solid region that's bounded by the region R and the surface. So this is the stronger form of Fubini's theorem, which tells us that a double integral may be evaluated as an iterated integral with either order of integration. And this is important because one of these integrals may be easier to evaluate than the other, depending on the complexity of the function. We can generally use two methods to find the limits of integration for many different regions in the plane. So for example, if we have this triangular region with one boundary line defined as y equals x, and this boundary line is at y equals 0, and suppose this boundary line is at x equals pi on 2. So the first method involves using horizontal cross-sections to evaluate the double integral of the function over the area of the region. So using the horizontal cross-section method, we first integrate our function with respect to x. So in 3 dimensions, our region in the plane looks something like this. So we have y equals 0, x is equal to pi on 2, and this is our line y equals x. So by taking this horizontal cross-section parallel to the x-axis, our cross-section looks something like this, being normal to the y-axis, and we break this up into thin rectangles And we're integrating from x equals y. So that's our left hand limit of integration. And our right hand limit of integration is at x equals pi on 2. And then integrating the result with respect to y, then we're summing up the volumes of these cross sections from y equals 0 to the y limit that includes all of these horizontal lines of this cross section. So when x equals pi on 2, y is equal to pi on 2. And that's our other limit of integration. So essentially the volume of our solid above this region looks something like this. So that's what our solid region looks like. Now in a similar way, we can choose vertical cross sections and evaluate the integral of our function with respect to y first. So we're integrating from y equals 0 to y equals x. So essentially these cross sections are parallel to the y-axis. And integrating the result with respect to x, we include all these vertical cross sections from x equals 0 to x equals pi on 2. So by Fubini's theorem, these iterated integrals give the volume of the same solid region that's bounded by the planar region and the surface z equals f of x and y. So given the function's continuous, these integrals are identical. So as an example, the function defining this surface is sine x on 4 plus sine y on 2 plus 2, and we'll integrate with respect to x first. So we're integrating from x equals y to x equals pi on 2. And then we integrate the result with respect to y from y equals 0 to y equals pi on 2. So what we get is minus cosine x on 4 plus sine y on 2 by x plus 2x, and that's evaluated at x equals y and x equals pi on 2, and this result's integrated from y equals 0 to pi on 2 to give the volume of the solid. So cosine pi on 2 is 0, and for the second term we have pi sine y on 4, and the third term gives pi. And then we have minus cosine y on 4 minus y on 2 sine y minus 2y. And that's integrated over y from y equals 0 to pi on 2. So these integrals are straightforward to evaluate, except the integral of this term, where we'll use integration by parts by setting u equals y. So du is equal to dy, and dv is equal to sine y dy. So therefore v is equal to minus cosine y. So uv is minus y cosine y, evaluated at y equals 0 and pi on 2, and minus the integral of v du, which is minus cosine y dy, evaluated from y equals 0 to pi on 2. So this integral gives minus pi on 2, cosine pi on 2, which is 0, and minus 0 by cosine 0. So this term drops out. And this integral evaluates the sine y, evaluated at 0 and pi on 2. So sine pi on 2 is 1, and sine 0 is 0. And evaluating the remaining terms, what we get is minus pi on 4 cosine y plus pi y plus sine y on 4 minus 2y squared on 2. And that's evaluated at y equals 0 and pi on 2. So what we get is minus pi on 4 by cosine pi on 2, which is 0, plus pi squared on 2, plus 1 on 4, minus pi squared on 4, and cosine 0 is 1, so we get plus pi on 4, minus 0, minus 0, plus 0. And we evaluated this integral by parts, which gave 1, so we have minus a half by 1, which is minus a half. So therefore the volume of our solid region is 2 pi squared on 4 minus pi squared on 4, which is pi squared on 4, plus pi on 4, plus a quarter minus 2 quarters is minus 1 quarter. And I encourage you to evaluate the integral with respect to y first, and you should get the exact same result, being the volume of this solid region. If we have two continuous functions of two variables, being f and g of x and y, defined on a bounded region R, then the following properties of double integrals hold. And one of those is the constant multiple rule. So if we have the integral of a constant multiplied by the function of x and y over the area of the bounded region, then we can take the constant outside the integral and multiply it by the double integral of the function over region R. And we also have the sum and difference rule. So given a double integral of the sum of a function f and a function g over the area of the region, then that's the same as evaluating the double integral of the function f and the double integral of the function g. And similarly with the difference rule, if we integrate the difference between the two functions, then that's the same as subtracting the integral of g from the integral of f. Now the additivity property states that if we have the double integral of a function f over a region R, and if the region R is the union of two regions that are not overlapping, so for example, if we break this region up into regions 1 and 2, then we can evaluate the integrals over each of these regions separately and add the results together. So we have the double integral of the function over region 1 plus the double integral of the function over region 2. So note that the boundary between the two regions must have a finite number of line segments or smooth curves. So for example, if we chose to evaluate the integral of the function over region R using vertical cross sections, then given the equation of this line is y equals x, for example, and the equation of this line is y equals 1 minus x, then we can't evaluate the integral over region R using a single integral. But if we chose horizontal cross sections, then we can evaluate a single integral over this region. Recall that for a general region that's bounded in the xy plane, we use the limit of the Riemann sums to obtain a double integral of a function of two variables over the region. And for a positive function, this gave the volume enclosed by the region in the plane and the surface defined by the function. Now if we take this function equal to 1, then we get a plane z equals 1. And therefore this integral becomes a double integral over the region. So this is essentially the area of a closed bounded region R in the xy plane. Recall the mean value theorem for an integrable function of one variable, which gave the average value of the function on a closed interval AB. So essentially the value of the function at C gives the area in this green rectangle, which is f of C by B minus A, and that's equal to the area under the curve, given by the integral. So we have the integral of f of x over x from A to B. Now in a similar way, we can obtain the average value of the function over a region in the xy plane. So suppose the average value of the function is at some point in a region with coordinates xa and ya. Then evaluating the function at this point, we get f of xa and ya, and then multiplying this by the area of the region is equal to the volume of the solid region bounded by R and the surface. So that's given by the double integral of the function over R. And then dividing through by the area gives the average value of the function over the region R. So that's 1 over the area of the region by the double integral. And we can see the similarities to the mean value theorem for functions of one variable. Sketch the region of integration and evaluate the integral. So we have x between 0 and pi, and y is between 0 and 2x. So 2 multiplied by pi is 2 pi. So we have a triangular region that looks like this. Now if we first choose to integrate over x, then sin x on x cannot be written in terms of elementary functions, so we can't integrate it. So what we'll do first is integrate our function over y first, and then integrate the result over x. So in other words, we're going to use vertical cross sections. And given this line is defined by y equals 2x, then we integrate from y equals 0 first to y equals 2x, and then we integrate from x equals 0 to x equals pi to include all those vertical cross sections. So what we get is sin x on x multiplied by y evaluated at 0 and 2x, and we integrate the result over x from 0 to pi. So we get 2x on x sin x, which is 2 sin x, minus 0 by sin x on x. And that's integrated over x from 0 to pi. So we'll take 2 outside the integral, and evaluating this gives minus cosine x. And we evaluate this at 0 and pi. So minus cosine pi is minus minus 1. So we get 2 by 1, and minus minus cosine 0, which is plus 1. So the integral evaluates to 4. Write an iterated integral using both horizontal and vertical cross sections. So x is between 1 and e squared, and y is between 0 and a natural log of x. So the natural log of 1 is 0, and a natural log of e squared is 2. So our curve looks like this. And this here is our region. So we have this curve defined by y is equal to the natural log of x. So using horizontal cross sections, we first integrate our function with respect to x. So our left-hand limit of integration is obtained by solving this equation for x. So taking e to the power of both sides, we get x is equal to e to the y. And our right-hand limit of integration is e squared. And then we integrate this result over y. From y equals 0 to y equals 2. And now using vertical cross sections, we first integrate our function with respect to y. So here we're integrating from y equals 0 to y equals the natural log of x. And then we integrate this result over x. From x equals 1 to x equals e squared. Find the volume of the solid region bounded above by the paraboloid and below by the given triangular region. So the triangular region is bounded by the line y equals x, y equals 0, and x plus y equals 1, which is another line with a negative slope and a y-intercept of 1. So when x equals 1, y equals 0. So the line looks something like this. And this here is our region R. So if we used vertical cross sections, we need to break this region up into two regions, because the limits of integration would be different. Given that this line is y equals x, and this line here is y equals minus x plus 1. So therefore what we'll do is use horizontal cross sections and first integrate our function, being the function for the paraboloid, with respect to x. So our left-hand limit of integration is x equals y, and our right-hand limit of integration is x is equal to 1 minus y. And then we integrate this result with respect to y from y equals 0 to this point, so we include all the horizontal cross sections. So if we substitute x is equal to y in this equation, we get the y coordinate of the intersection point, which is 1/2. So that's our other limit of integration. So evaluating the inner integral, we get x cubed on 3 plus y squared x plus x evaluated at y and 1 minus y, and we integrate this result from y equals 0 to y equals 1/2. So that gives 1 minus y cubed on 3 plus y squared by 1 minus y plus 1 minus y minus y cubed on 3 minus y cubed minus y. And that's integrated from y equals 0 to 1/2. And now if we evaluate this integral while making some simplifications, we get minus 1 minus y to the 4 on 12, and this term is minus y cubed. Minus y cubed gives minus 2y cubed, or minus 6y cubed on 3, and minus 6 minus 1 is minus 7y cubed on 3. So what we get is minus 7 y to the 4 on 12. And then we have a y squared term, so that gives y cubed on 3. And minus y is negative 2y, so that gives negative 2y squared on 2. And finally the integral of 1 is y. And that's evaluated at 0 and 1/2. So 1 minus a half is 1/2 to the power of 4 is 1 on 16. So that gives minus 1 on 16 by 12. And minus 7 by 1/2 to the 4. So that also gives 16 on 12 in the denominator. Plus 1 on 8 on 3, which is 1 on 24. Minus 1 on 4, plus a half. And then we have minus 1 on 12. And substituting 0 in the remaining terms gives 0. So this first term gives minus 8 on 16 by 12. So 8 on 16 is a half. So that gives minus 1 on 24. Plus 1 on 24. And then we have minus 3 on 12. Plus 6 on 12. Plus 1 on 12. So as we can see, these terms cancel. And what we get is minus 3 plus 6 is 3. Plus 1 is 4. On 12 is a third. Given the following integral, sketch and find the area of the region. So integrating with y first means we're using vertical cross sections, which are bounded below by sine x and above by cosine x. So recall that sine x is a maximum at pi on 2, where it's equal to 1, and at pi on 4, it's equal to 1 on root 2. So it looks something like this up to pi on 4. And cosine x is also 1 on root 2 at x equals pi on 4, and looks something like this. So it's a maximum when x equals 0. So this is our region, bounded above by y equals cosine x, and below by y equals sine x in the xy plane. So evaluating the iterated integral, we evaluate the inner integral first. So that evaluates the y at sine x and cosine x. And we integrate the result from x equals 0 to x equals pi on 4. So we get cosine x minus sine x integrated from 0 to pi on 4 with respect to x. So this evaluates the sine x minus cosine x at x equals 0 and pi on 4. So what we get is 1 on root 2 plus 1 on root 2 minus sine 0, which is 0, minus cosine 0, which is 1. So this evaluates the 2 on root 2 minus 1, which is root 2 minus 1. Find the average height of the paraboloid over the given region. So recall that the average value of the function at some point in the region is equal to 1 over the area of the region by the double integral of the function over the area of the region. So we can evaluate this as an iterated integral. So we can first integrate the function for the paraboloid with respect to x or y. So here we're integrating over x from x equals 0 to 1. And then integrating the result over y from y equals 0 to y equals 1. So the area of the region in this case is simply 1 by 1, so we can ignore this term. And now evaluating the inner integral, we get x cubed on 3 plus y squared x plus 2x evaluated at x equals 0 and 1, and we integrate the result over y. So what we get is 1/3 plus y squared plus 2 integrated over y from y equals 0 to y equals 1. So 2 is 6 on 3, and 6 on 3 plus 1/3 is 7/3. So this evaluates as 7/3 y plus y cubed on 3. And we evaluate this at y equals 0 and 1. So that gives 7/3 plus 1/3, which is 8/3, being the average height of the paraboloid over the given square region.